This is a lesson on Routh stability criteria. And Routh stability criteria has to do with determining whether the poles of a transfer function have real parts that are greater than 0. And if you recall that if we place the poles of a transfer function on the S-plane, we have real and imaginary axes, that for stability we need to have all of our poles to the left of the j omega axis. All right, and this would be called absolute stability. So we'd say pi, these are the poles for I equal to 1, 2 to n, are going to all have real parts that are less than 0. Now we can also have what is known as critical stability. Critical stability includes the j omega axis. So critical stability, and here the real part of each of all poles is less than or equal to 0. So as an example, if we have some transfer function h of s is equal to 1 over s times s plus 1, then we have poles at 0 and at minus 1. And this is critically stable because if we apply a unit step, which is a 1 over s, to this system, the output c of s is going to be equal to 1 over s, s plus 1, and then it'll be times the input, which is 1 over s. And when we do partial fraction expansion, this is going to expand into some constant over s squared plus b over s plus c over s1. Right? We can find a here. A is going to be equal to 1 over s plus 1 with s equal to 0, so it's 1. So this term here, 1 over s plus or s squared, has an inverse Laplace transform that is t times the unit step. So in other words, it just grows in time. So it's unstable. Now this wouldn't be the case if we did not apply a unit or a constant input, right? But it's actually because the pole of the excitation is also a pole of our transfer function right here. And so the same is true if you have a transfer function, say 1 over s squared plus 1, it would have poles at plus or minus j. So they're on the j omega axis over here. And so this would be an oscillatory natural response. It would be a sine or cosine of 1 times t. So sustained oscillation, but it doesn't grow unless the excitation r of s actually has these same poles. In other words, if it's actually a sinusoid of a frequency 1 radian per second, in which case then the response or the output would be a linearly growing sine wave. And so again, it would be unbounded. So that is a critically damped system. And now we also have what we'd call relative stability. And relative stability is the case where not only do we have all the real parts of our poles less than 0, but also subject to additional transient performance criteria. So this could be where we specify the rise time or the settling time, things of that nature. What the Routh Stability criteria is useful for doing is helping us determine whether the system is absolutely stable or not. It is not so useful at studying relative stability, although it does have some limited ability to do that. And the usefulness of the Routh Stability criteria is that you can determine if any of the poles of the system have positive real parts without actually ever factoring the denominator in your transfer function. Okay, so let's start off by looking at some polynomials here. So we'll say we have a transfer function g of s that is going to be of the form b of s over a of s. And b of s would be of the form b0 s to the m plus b1 s to the m minus 1 plus dot 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 all the way to b sub m minus 1 s times or plus b sub m. All right, and then this will be over a0 s to the n plus a1 s to the n minus 1 plus dot 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 plus a n minus 1 times s plus a0. And so we're looking for whether the polynomial a of s has any positive real parts. So consider a of s in general. And specifically, we'll look at a couple examples now before we present the technique formally. So notice if we have a polynomial, a of s, that has poles of plus 1, or poles at minus 1 and minus 2. Right, if we expand this, we'll get s squared plus 3s plus 2. And so the coefficients here are 1, 3, and 2. If we have a polynomial s minus 1 times s plus 2, so in other words, there is a pole or a root that is positive, then we would have 1 times s squared plus s minus 2. And notice here that we have plus 1, and minus 2. So here all coefficients are greater than 0, and here all coefficients are not greater than 0. And we can look at this a little more generally if we have a polynomial of the form, let's say s squared plus bs plus c, and we solve for the roots. The roots are going to be equal to, using the quadratic formula, minus b over 2 plus or minus square root of b squared over, actually it'll be b over 2 squared minus 4ac over 4, that'll be just c. Okay, so for poles P1 and P2 to have real parts less than 0, then we have some constraints on B and C. B must be greater than 0. And furthermore, notice that if C is negative, then this radical term here will have a magnitude that is, or will have a value that is actually greater than b over 2. And so when you add that to our first term, minus b over 2, the resulting pole will actually be positive. So therefore, we also need that need to have c being greater than 0. All right, and then more simply, if we just have a polynomial that's s plus d, then we require that d is greater than 0 for the pole to be less than 0. So now we can put these two together, and we can say, what if we have a polynomial that is s squared plus bs plus c times s plus d? Well, if b and c and d are all positive, and these are required for the roots associated with each of these terms to have negative real parts, then the expanded form of the product of these two terms is going to also have coefficients that are only positive. So the conclusion that we draw once we realize that actually any polynomial as, regardless of its order, is ultimately factorable into complex conjugate pair terms, which is what we have here, this first one, or just simple root terms. And so in order for all of the roots to have negative real parts, all ai's, okay, all coefficients of a of s, where a of s is equal to a0 s to the n plus a1 s to the n minus 1 plus dot 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 a of n minus 1 s plus a of n, all ai's must be, just a second there, must be positive. Okay? So that's a necessary condition. So let me recap that. Okay, for stability, I'll say for absolute stability, one, AI must be greater than 0 for I equal 0, 1, 2, all the way up to n. Now that's a necessary but not sufficient condition. Okay, 2, then we have to make further tests satisfy further tests on A of S using the Routh Stability criteria, which we have yet to describe. Now note, if any AI is less than is less than or equal to 0, then A of S has at least one root with the real part greater than or equal to 0. So if we go back to our S-plane here, for critical or for absolute stability, we want to stay off of the j omega axis. Okay, and what this says is that if any of the coefficients on the polynomial of the polynomial A of S are not positive, then there will be at least one root that will lie either on the j omega axis or to the right. Okay, at least one root will lie in this region. Now, if we find, therefore, if we see that one or more of the coefficients in A of S is negative, and we're simply trying to determine if the system is absolutely stable. Then we stop at this point and we say there's no point going further because the system cannot be absolutely stable if there are any coefficients that are not positive, and that includes coefficients that would be 0 as well. Okay, so assuming that a of I is greater than 0 for I equals 0 to n in A of S, then we want to apply the following test. Then apply the following Routh Stability criteria test. Okay, and this is how we set this up. It's better shown by example. So if I have a polynomial, let's say AS equal to, we'll say that it's A0 S cubed, and we'll say S4. S4 plus A1 S cubed plus A2 S2 plus A1 S plus, A3 plus A4. Okay, then what we do is we are going to label or set up n plus 1 rows as follows. First row we're going to label s to the 4th because it's the highest power in this polynomial. Next s cubed, next s squared, s to the 1st, and then s to the 0. Then up in the first row we're going to place all the even terms, and they're actually the even coefficients of A, so it'll be A0, A2, and A4. And then we put the odd terms in the second row, so that'll be A1, A3. Alright, so now we're set up. I'm going to just do a little dotted line just to indicate that the top two rows always specify the coefficients in the polynomial A of S, and the remaining polynomials, or the remaining entries in this table that we're making, are going to be computed from those first two rows. And this is how we compute them. We will compute this value here in the first column, third row, by taking a product, actually the difference of a product. We're going to take A1 times A2, that's this product here, minus A0 times A3. And then we divide all of that by A1. Okay, so that's our first term. I'll set him over, call him B1. Then B2, which is this term here, is defined as, and here we take, I'll do them in a different color, we take A1 times A4 minus, and then here we have a 0, so it'd be 0 times A0. 0 times A0, and all of that is divided by A1. It is not divided by A3, so we always go back to the first column. Next, we fill out the fourth row. We have C1 here. And C1 is going to be equal to B1 times A3 minus B2 times A1 divided by B1. And then C2 will be B1 times 0 minus 0 times A1, all divided by B1. So this will actually be equal to 0 here. And make sure I did that right. And then lastly, we would have D1 here, and D1 is going to be equal to C1 times B1, or B2, I'm sorry, minus B1 times 0, all of that divided by C1, and so it's simply equal to B2. Okay, now we fill all this out and we stop at this point, and then the final step is to look at the first column in this table and count the number of sign changes. Okay, the number of sign changes equals the number of roots having positive real parts. So in other words, roots that are over here on the S-plane. Not even on J omega, but actually positive. And it doesn't tell us what the roots are. We don't actually care in this case. It just tells us how many we have. Okay, let's try this out with an example. So let's say that we have A of S is equal to S4, S to the fourth, plus S 2S cubed, plus 3S squared, plus 4S, plus 5. And we say we note that all coefficients are greater than 0. Now that doesn't mean that we're guaranteed that it's stable, but if they weren't all greater than 0, then we'd be guaranteed that it would be not absolutely stable. Okay, so let's set things up. We've got S to the 4, S to the 3, S squared, S to the first, S to the 0. In the first row, we're going to put the even terms. So that's going to be 1 for S to the fourth, 3 for S squared, and 5 for S to the 0. In the second row, we'll put the odd terms. So that would be, here this 2 for S cubed, and then 4 for S to the first. And then we're done. So now we will compute the remaining rows from the first two rows. So our first term in the third row is going to be 2 times 3 minus 4 times 1. So that's 2 times 3 minus 4 times 1 divided by 2. So that's 6 minus 4 is 2 divided by 2. That's equal to 1. So let me just write that there. 2 times 3 is 6, minus 4 is 2, divided by 2 is 1, yes. Then our second term is going to be 2 times 5 minus 0 times 1, all divided by 2. So that gives us 5. And we don't have a term out here because it would be 0. Okay, then we go to the next row, and we would have 1 times 4 minus 5 times 2, all divided by 1. So that's 4 minus 10 is minus 6 divided by 1. That's minus 6. And then here we would have 1 times 0 minus 0 times 2 divided by 1. Of course, that's going to be 0. So 0. And then the last row, we're going to have minus 6 times 5 minus 1 times 0 divided by minus 6. And that gives us 5. So we have a sign change from here to here, from a 1 to minus 6, and a sign change from a minus 6 to a plus 5. So we say, therefore, there must be 2 roots with positive real parts. Now, something that you can do to sometimes simplify the arithmetic is that you can divide or multiply any row by a positive value. So here we can divide by positive value of 2. So if we redid this, we would have 1, 3, 5, and then 1, 2, 0. And if I compute the next row here, it's going to be 1 times 3 minus 2 times 2 divided by 1. So that's 3 minus 2 over 1. That's 1. And the value here is going to be 1 times 5 minus 1 times 5 minus 0 times 1 divided by 1. So that'll be 5. And now in this spot here we have 1 times 2 is 2, minus 1 times 5 is minus 3, divided by 1 is minus 3. And lastly, minus 3 times 5 is 15, minus 0 times 1 is 15, divided by minus 3 is 5. And so we still see that we have a sign change and a sign change. So we get the same result. Okay, I've jumped over to some hand notes that I've written and that will be posted. They're part of the time domain analysis notes that go along with Untitled Chapter 5. This version that I have here is version 6, so make sure you're looking at that version because I've made a few corrections and additions to this section, or version 6 or newer. So I just want to point out that if you want to go over some of the points, you can do that here. I'm not going to repeat that, but I want to go to some examples and just walk through some examples rather than working them out. And you can go back to the notes and look at them if you care to. Okay, so one of the things that's useful in the Routh Stability criteria, of course, is when you apply it to control systems. And we've already seen that when you are trying to control the response of a closed-loop system, you will add in some kind of a controller. It might be something that's as simple as just a proportional term, or maybe it would involve an integral term as well, and even a derivative term. So although we haven't studied these really in any depth, we did mention that there is such a thing as a PID controller, a proportional integral derivative controller. And in this example here, just a second here. Okay, in this example here, we see that we have a system that has a proportional and integral controller. And that's not really important here other than just to show that it is in fact a a system that has a controller on it. The physical plant here, you might recognize with the rotational inertia and the viscous element B, that this is a servo system. So it's some kind of system that's rotating, and the output is likely going to be the angular displacement of the system. And the question is, we're wondering, is there a range of values for Kp, the proportional term, and Ti, the integral term, that we need to watch for in order to avoid instability. So we can set up the Routh stability criteria using the denominator of our transfer function. And so here you see it in action, where it's been populated with ultimately parameters from the system. So once we evaluate this, we see that we have our four terms in the first column. We have J, we have B, we have this difference divided by B, and then we have Kp over Ti. So J and B are both going to be positive. So that means that if we want all of our roots to have, all of our poles to have negative real parts, then we have to make sure that this difference over B and this Kp over Ti are both positive, because J and B are positive, and we don't want any sign changes. So we can do a little arithmetic on our third row here, and we find that there is a constraint on Ti that it must be greater than the quotient of the rotational inertia divided by B. And then because Ti is positive, based on that constraint, we now can say that using the last row, that Kp must also be 0, such that the quotient of Kp over Ti would be positive, and therefore there would be no sign change going down the first column. So that's an example of using the Routh stability criteria in a control system. And another usefulness is that you can actually assess relative stability. It's limited, and I mentioned at the beginning that its Routh stability criteria is not used, its strength is not relative stability, but rather just is a system absolutely stable or not. We will look at other tools eventually for assessing relative stability. But there is a way that you can assess relative stability, and one of your homework problems will actually ask you to do this. So the trick is that if we recognize that what the Routh stability criteria tells us is whether any poles or any roots of a polynomial are greater than or equal to 0, or have real parts that are greater than or equal to 0, then if we replace s in our original polynomial here, as an example, with a new s, call it s hat, which is equal to s minus alpha, and we substitute this s hat plus alpha into our original polynomial, and then we evaluate the Routh stability criteria for s hat, then if we look at the first column, which is what's being done here as we work this out, and we consider what would it take to cause a sign change, then the parameter values that would cause a sign change as we go down that first column would correspond to the case where at least one pole in our system has a real part that is actually equal to alpha over here. Okay, and we find that in this case that B, in order to stay, let's say, to the left of this line alpha, B must be greater than minus 2 alpha. Now typically alpha here is going to be negative, right? So let's say alpha was minus 1. Okay, minus 1. Then B would have to be greater than 2. And then C has to be greater than minus alpha squared minus alpha B. So you see here that we can check the relative stability, although all we're really doing is we're saying we can test whether or not all of the real parts of, if all of the poles are to the left of a vertical line equal to alpha. We can't do things like where we want to check, for instance, if it's a second order system, what is the damping ratio, right? The position or the distance of all the poles to the left of the imaginary axis actually control the settling time of our system, but we need to know more than that in order to determine like the overshoot or the damping ratio. That we can't learn that from the Routh stability criteria. Now there's a couple special cases. I'll point out that really two cases that we look at. Okay, and one of the cases is, what do you do if one of the rows, as you go through evaluating Routh stability, one of the rows in your table comes back with all zeros? Okay, that would be one problem. Another one, which maybe I should consider first, because it's a little simpler. Yeah, let's consider the other one first here. Let me switch over to my other set of notes here. Get a clean sheet. Okay, I'll just work this example. Let's consider the case where we have a of s is equal to s cubed plus 2s squared plus s plus 2. So s cubed, s squared, s to the first, s to the 0, 1, 1, 2, 2. Now we go to evaluate the first entry in third row, and we get 2 times 1 minus 2 times 1 divided by 2, and that is 0. Okay. Now if we proceed from here on, we have a problem, because when we do 0 times 2 minus 0 times 2 and we divide by 0, that's not good. We don't want to divide by 0. So what we do is, when this is 0, we actually replace it with epsilon. Okay, and then we proceed. So here we're going to, as we proceed, we will have epsilon times 2 minus 0 times 2. So epsilon times 2 minus 0 times 2 divided by epsilon. And that gives us 2. Okay, so I'll erase that, I'll put 2. So what we really have is, we have positive, 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 a 0, and then positive. And what the Routh stability criteria says, that if there is no sign change, no sign change from above this 0 to below, that means that therefore there is a pair of complex imaginary roots. In other words, they lie on the j omega axis. All right, so this means not absolutely stable. But it would be critically stable. Critically stable. Okay, so that's one scenario. Now let's consider another polynomial. Here we have s cubed minus 3s plus 2. So we start off s cubed, s squared, s1, s0, put 1, and then minus 3. For second row, the second power, s squared term, notice is missing. There's actually we could actually write in here plus 0 times s squared. So we put a 0 here, and then we have 2. Now because we have a 0 in the first column, what we need to do is, again, replace that with epsilon. And now we proceed. So we have epsilon times minus 3 minus 2 divided by epsilon. So that's going to be minus 3 over negative, minus 3 minus 2 over epsilon, minus 3 minus 2 over epsilon. And then we will have, in the next row, we'll end up with 2. Okay, so now as you let epsilon go to 0, as epsilon goes to 0, then we end up getting a negative infinity, right? Negative sign. So we have a sign change from above the 0 entry to below it. We have a sign change. And that means that we have, therefore, 2 roots with positive real parts. With positive real parts. And in fact, the roots, in this case, if we factor this out, we find that this is equal to s plus 2 times s minus 1 squared. So it has roots at minus 2 and at 2 roots right at plus 1. Okay, so that's one special case. Now the other special case is as follows. Let me find the example. So let's suppose we have a of s equal to s5 plus 2s4 plus 24s3 plus 48s squared minus 25s minus 50. Now notice right away, these are not all positive, so this is therefore not absolutely stable. So if we're only looking at absolute stability, then this special case appears to not even be necessary to consider, but it's given in the book, and so I'm going to give it to you here. So let's get this set up. So really all we're trying to answer here is the system unstable, or is it merely critically stable? Because at best it will be critically stable. So we have 1, 24, and minus 25. We have 2, 48, and 50. And to simplify things, let's divide through by 2 on this second row, and so we'll have 1, 24, and 25. And now we start filling this out. So we have 1 times 24 minus 24 times 1 over 1, and so that is 0. Next we have 1 times minus 25 minus 25 times 1 over 1. That's also 0. And when we go to the next row, okay, so we're done there. Now the problem is that we have all zeros in a given row. Okay, so that's the special case. What do you do when you have all zeros in a given row? Well, you take what's called the auxiliary polynomial. This right here is the auxiliary polynomial. So call it P of s, and it's equal to s to the 4th plus 24s squared plus 25. And then what we actually do is we take the derivative of this auxiliary polynomial and we plug it back in, and we replace the zeros with the derivative. In this case it's going to be 4s to the cube, 4s to the 3rd, plus 48s plus 0. So we'll put 4, and we'll put 48. And then we proceed. So I have 4 times 24 minus 48 divided by 4. That's 24 divided by 4, or 6. If I did that right. Oh, wait. We'll even simplify this first. We'll divide this by 4 to get 1. Divide this by 4 to get 12. Okay, so we have 1 times 24 minus 1 times 12. So that's 12. Here we have 1 times 25 minus 0 over 1, so that's 25. Oh wait, I'm sorry, there's a minus 50 up here. That's a minus 25. So that means this is a minus 25. And then we have 12 times 12 minus 25 times 1 divided by 12, and that turns out to be 14.08, and then the last entry is minus 25. So we have a sign change in our last two rows here. One sign change, and so therefore we have one root with a positive real part. Okay. Interestingly, we can actually find the roots of the auxiliary polynomial. So we can write this as s squared plus 24, s squared plus 25. And so we can use the quadratic formula to solve this if we need to, but in this case we don't even need to. It's s squared plus 25 times s squared minus 1. Oh yeah, my auxiliary polynomial is actually a minus 25 up here. Minus. That's minus. There we go. Okay, and the roots for this are s is equal to plus or minus j5, and s is equal to plus or minus 1. And it turns out that the roots of this auxiliary polynomial are also the roots of the original polynomial. So it can be shown here that the roots of a of s are s plus j5, s minus j5, s plus 1, s minus 1, and then finally the other one is s plus 2. So we found the first four just by looking at the roots of the auxiliary polynomial. On the s-plane, or on the complex plane, we would have plus and minus 1, plus and minus j5, and then minus 2.